Okay, today's lesson is 12.1b. We are finishing up estimating limits graphically that we started in the previous day. We are concentrating on the second part of this lesson, which is estimating limits of functions at infinity. So to remind you, okay, what we have done thus far is we've described a function, how it behaves as x approaches a fixed value of c. And earlier in the year, technically, in section 1.3, we learned about limits and how they can be used to describe the end behavior of a function. That is, how a function behaves as x increases or decreases without bound. The notation that we used, if you remember, we had the limit as x approaches infinity of f of x equals L. That was our right arrow, or how we described our graph as x increases. And if x decreases, then we had the limit as of f of x as x approaches negative infinity is another limit. So these were the two. This was basically saying, what's the right arrow doing? What's the left arrow doing? Okay. Now, the two ways that we're going to use infinity in our limits that we're talking about today, we have one where x equals c happens to be a vertical asymptote of our graph, in which case we have a left-sided limit approaching positive or negative infinity and a right-sided limit approaching positive or negative infinity. Remember, that's what that little notation above the c is. This is coming from the left and this is coming from the right. Okay. The other one you'll have is that's not x equal to c, but y equal to c, and that would be a horizontal asymptote. And in this case, our c and infinity are going to switch places, and we're going to say, what's the left arrow doing? So what is the limit of the function as x approaches negative infinity equal to some value c? What is the limit as x approaches positive infinity is c also. That's when we have a horizontal asymptote. And we talked about that a lot, y'all, when we talked about rational functions, and that's when we used Betsy, Bobo, and Botu, which I will talk about more later, but it's just kind of nice to see the connection when we're looking at the graphs. Okay, so the first one that we have, we're estimating the limit as x approaches infinity of 1 over x to the fourth minus 3. Again, y'all, we are looking at the graph, okay? So you're going to pull this up in ClassCalc or Desmos, however you want to. And when you see this type on a function, okay, when you see this graph on a function, and you can see we're looking for x approaches positive infinity. Well, positive infinity is on the right. So when I'm looking at this graph, I can see that it is approaching this number. And that's why the tables sometimes come in handy. If you remember, we made these earlier in the year, and these numbers are getting really, really big because those numbers are going to infinity. And you can see clearly what's happening is that the numbers are approaching, the y value is approaching negative 3. So we say the limit of this function as x approaches infinity is negative 3. Okay. Let's go on. I was going to tell you about, but we'll talk about the Betsy, Bobo, Botu later. Next section. Okay, this next one, the limit as x approaches negative infinity of e to the x. Again, easiest when you have a picture. Okay, x approaching negative infinity. Negative infinity is all the way to the left on my number line. So what is happening to this graph? And you can tell by looking at it that it's getting closer and closer to the x-axis, which is when y equals 0. Now, if you did happen to look at the tables, y'all, that's a really small number. And who knows what this is scientific notation. And I'm telling you right now that had e to some negative number because it was really, really, the decimal went over more places than that is showing right there. So you can see as we get bigger and bigger, it's getting to 0. Okay. And we'll do this last one and then we'll talk. The limit as x approaches infinity of the sine of x. Okay, here is my graph of the sine of x. Okay, well, as x goes to infinity, I'm going this way, and it's bouncing between positive 1, negative 1, positive 1, negative 1, so forth and so on. And so I'm sure you remember that means the limit does not exist because it doesn't approach the same number. It's oscillating is what we talked about before. Okay. Looking at these numbers, it's going negative, negative, and then 0, and then negative, and then positive. So it's not going to the same number. One of the things you have to be careful about these positive and negatives if they're both getting smaller and smaller, but they're not. So, and again, it's easiest, I hope you can see and believe me that it's easiest to determine the limit when you're looking at the graph of a function. All right, so the last two things I want to talk about is just some real world examples because this would be a case where they're kind of applicable. So this first one that we have, the typical voltage V supplied by an electrical outlet in the United States can be modeled by the function V of t equals 165 sine of 120 pi t, where t is the time in seconds. Estimate the limit of the function as t approaches infinity, if it exists, and interpret your results. Okay, so this is my function that I'm going to put in, and if you put it in a Desmos or class calcul, you can't put t, you have to put x. You would put y equals this. This is a normal sine function. 120 is a number, pi is an irrational number, and that's x. So it's kind of like y equals a sine bx. So this is my amplitude. That's how tall it gets. So if you put this in, okay, I'm looking for the limit as x approaches infinity. So I went ahead and graphed it, okay? That's it. Remember I told you had to put t in for x. But if you can see, this thing is going nuts, back and forth, just like any sine graph that we've had, okay? So you know that the limit does not exist, okay? Now, interpret you. What does that mean? That means that the voltage will fluctuate between negative 165 and 165 because that was the amplitude of my sine graph. Okay, last problem. Short video, then you can get your homework done. Fruit flies are placed in a half-pint milk bottle with a piece of fruit and a yeast plant. The fruit fly population after t days is given by P of t equals 230 over 1 plus 56.5 e to the negative 0.37 t. Estimate the limit as t approaches infinity of P of t, if it exists, and interpret your result. So here, I don't know how many of y'all know, but this particular format of a function is called a logistic function. So it's doing this. It's starting down here, and then it grows, and then it levels off. Okay? So when you look at your graph, it might look like it's 240, but when you look at it, I'm telling you right now, it's going to be that number if you zoom in on your graph or look at the tables. So the limit of the function as I'm going to infinity, which is that way on my graph, is going to be 230. And what does that tell us? Over time, the fruit fly population will approach a maximum of 230 fruit flies. Wonderful. That is the end of estimating limits graphically. I put the table in there for you too. If you have any questions, please don't hesitate to email me or set up a Google Meet. Thank you so much, and y'all have a great day.